Welcome, everyone! In this explainer, we're going to dive into something that's, well, fundamental to all of physics: measurement. We'll kick things off with a skill you use every day: estimation. And then we'll get into the system that lets scientists all over the world speak the same language: the SI units.
So, here's the plan. First, we'll talk about the art of making a really good scientific guess. Then, we'll lay down the foundation with the 7 SI base units. After that, we'll see how we can build bigger ideas using derived units. And to wrap it all up, we'll take what we've learned and apply it to some really big and really small questions.
All right, first up, before we even think about fancy lab equipment, let's talk about a tool that every single one of us has right here in our own heads: the ability to make a good, solid guess. You know, in science, we don't just call it guessing, it's estimation. And trust me, it's a super important first step for tackling some really tough problems.
Okay, so to really see what I mean, let's try a little thought experiment. How heavy is the air in a typical classroom? I mean, seriously, how would you even begin to answer that without, like, a giant scale? Well, this is exactly the kind of problem where estimation really shines.
Now, before we jump into solving that, let's be super clear on what we mean by estimation. This is not just a shot in the dark, right? It's a real skill. It's all about using what you already know to make a reasonable, calculated guess about the size or magnitude of something. Okay, so how do we do it? Let's break it down, step by step. First, we just estimate the size of the room. A normal classroom, maybe something like 5 meters by 10 meters with a 4-meter ceiling? Sounds about right. A quick calculation, and boom, that gives us a volume of 200 cubic meters. Now for step 3, we need something we might just know or it can look up easily: the density of air. It's about 1.2 kilograms for every cubic meter. So we just multiply that density by the volume we just calculated, and we get our answer: 240 kilograms.
And get this, that's what's so cool about this whole process. We just estimated the mass of the air in the room to be about 240 kilograms. Now, to put that in perspective, that's roughly the weight of 3 adults. How wild is that? We took a question that seemed impossible and, with a few simple steps, turned it into something we can actually picture.
And listen, this isn't just a fun little puzzle. Estimation is an absolutely crucial skill in science and engineering. Think of it like a sanity check. If you do a super complex calculation and your answer is way off from your initial estimate, you know you probably made a mistake somewhere. It's essential for planning projects and, for those times when you just can't get an exact measurement.
Okay, so estimation is great for getting us in the right ballpark. But for real science, close enough isn't going to cut it. We need precision. We need a system so that a scientist in Japan and a scientist in Brazil can compare the results and know they're talking about the exact same thing. That's where the International System of Units, what we all call SI units, comes in. It's the universal language of measurement.
And here's the amazing part. The entire vast language of physics is built on just 7 fundamental building blocks. That's it, just 7. You can see them here: length, mass, time, electric current, temperature, amount of a substance, and luminous intensity. Literally everything else we measure in the physical world is just a combination of these 7 basic ideas.
So this naturally splits all of our units into 2 groups. You've got your base units, those are the fundamental 7 we just looked at. Think of them like the primary colors or basic ingredients. They can't be broken down any further. Then you have derived units. These are what you get when you start mixing and matching the base units. A perfect example is speed. It's not a base unit, it's derived from length, meters, and time, seconds. Okay, so let's get our hands dirty and actually see how we build with these units. This is where it gets really interesting, because this is how we start describing more complicated but familiar things in the universe, like force and pressure, using just those 7 basic building blocks. Let's start with a big one: force. We all have an intuitive idea of what force is, right? It's just a push or a pull. But in physics, we need to be a little more precise. A force is any interaction that makes something with mass change its velocity. Basically, to speed up, slow down, or change direction. In a word, to accelerate.
And the way we write this idea down in the language of math is with one of the most famous equations in all of science: F equals ma. It's so simple, yet so powerful. It perfectly connects that physical idea of a push or pull to 2 things we can actually measure: an object's mass and its acceleration.
So watch how we get the unit for force. It's actually pretty slick. We just plug the base units right into the formula. Mass is measured in kilograms, acceleration is measured in meters per second squared. So the unit for force has to be a kilogram meter per second squared.
That's a bit of a mouthful, so we give it a special name, the Newton, which we write with a capital N.
All right, let's take it one step further and build on what we just did. Let's talk about pressure. Now, the key idea here is that pressure isn't just about force. It's about how concentrated that force is. Think about it. Pushing on your hand with your finger is one thing, but pushing with the same force using a needle point, that's going to hurt. That's high pressure because the area is so small.
And once again, there's a beautifully simple formula that captures this exact physical idea. Pressure equals force divided by area. It literally is force per area. So let's derive the unit, just like before. We already figured out the unit for force, right? That's the Newton. The unit for area is meter squared. So the unit for pressure is just a Newton divided by a meter squared. And just like with force, this unit gets its own special name, the Pascal, written as PA. See how we're building up, layer by layer?
Okay, theory time is over. Let's actually put these powerful tools, estimation and our understanding of units, to work. We're about to see how they let us get a handle on the mind-boggling scales of our universe, from the incredibly tiny to the unbelievably huge.
First, let's zoom way in. A single bacterium, right, has a mass of about 10 to the minus 15 kilograms. And a single proton, one of the building blocks of atoms, has a mass of 10 to the minus 27 kilograms. So the question is, how many of those tiny protons would you need to equal the mass of just one bacterium?
Well, the math is actually pretty straightforward. You just divide the bigger mass by the smaller one, and the answer you get is 10 to the power of 12. That's a 1 with 12 zeros after it, 1 trillion. A trillion protons inside one single bacterium. That's just amazing. Okay, now let's go from the micro to the macro. Let's go big. The diameter of our sun is about 10 to the 9 meters. That's a billion meters. And a single hydrogen atom is about 10 to the minus 10 meters across. So here's the question. How many of those tiny atoms would you have to line up, one after another, to stretch all the way across the sun?
It's the same idea, just with different numbers. We divide the big distance by the small one. The answer? 10 to the power of 19. I don't even know the name for that number off the top of my head. It's enormous. It's these kinds of simple calculations, grounded in our system of units, that let our brains even begin to wrap around scales that are just otherwise impossible to imagine. So think about what we've just done. We've seen how just 7 base units can be used to describe everything from a simple push to the pressure inside a star, and to measure things from the size of a bacterium to the size of the sun. It really leaves you with a final question to chew on, doesn't it? If we can describe all that, what other complex parts of our universe can we unlock and understand just by finding new ways to combine a meter, a kilogram, and a second?